Okay, in today's video, we're going to finish up going over this problem for induced voltage. So this is officially part 2 of this video. In part 1 of this video, which you can link to in the upper right-hand corner, we went over questions 1 through 4, where we determined and talked about the induced voltage and also the change in the magnetic flux. And this video, which is part 2, we're going to determine the magnitude and direction of the induced current, and then we're going to determine the magnitude and the direction of the force on this bar when we move this bar through this magnetic field, which has a magnetic field strength of 5 teslas. It's moving along these metal railings, which are attached to this resistor, which has a resistance of 5 ohms. And the magnetic field is directed into the page, as we can see by these X's, and we're going to move the bar 1 centimeter a second. Okay, the first thing we're going to do in this video is we're going to determine the magnitude and the direction of the induced current. Now, the magnitude is pretty simple. We're just going to use Ohm's law. That would be V equals I times R. We're going to rearrange that for the current, of course, which gives us the current is equal to the voltage divided by the resistance. And in the previous video, part 1, which you can again link to in the upper right-hand corner of this video, we determined that the magnitude of the induced voltage as this bar moves along those railings, we determined that the magnitude of the induced voltage is minus 7.5 times 10 to the minus 3 volts. We know the resistance is 5 ohms. We divide those two values and we get that the induced current is minus 1.15 times 10 to the minus 3 amperes. Don't forget this negative sign. This negative sign comes from Lenz's law, which we're now going to talk about when we determine the direction of the induced current. Okay, so this I think is probably the hardest part to explain of this whole thing. And what happens is this: we take this bar and we move the bar along those railings. As we do that, we're increasing the area of this loop of wire, but what we're really doing when we do that is we're increasing the amount of magnetic flux. We're increasing the amount of magnetic field that's inside this loop of wire. And again, the magnetic field points into the page. Now, the problem is that that loop of wire doesn't like that. It doesn't like things to change. What's changing is the amount of magnetic field that's directed into the page. So, according to Lenz's law, what that loop of wire is going to do, it's going to generate a current. So we're going to have an induced current in that loop of wire, and the induced current is going to produce a magnetic field that's directed out of the page. Because we're having more magnetic field into the page, and we kind of want to negate that or neutralize that, or we don't want that. The coil doesn't want that to happen, so it produces magnetic field that's directed out of the page. So that's the first thing, is we have magnetic field that's in, we increase the flux, the coil doesn't like that, so it produces a magnetic field to oppose that change. And the magnetic field to oppose that change is magnetic field directed out of the page. All right. Now what we have to do is we have to determine for this coil which direction would the current have to flow around this loop. Would it be in the clockwise direction or the counterclockwise direction, which would produce a magnetic field that would be directed out of the page when you're inside this loop. And the way we do that is we take our right hand. This is my right hand. We're going to use the right hand rule. This is kind of the right hand rule we use to determine the direction of the magnetic field or the direction of the current from a long straight wire. And I'm going to focus first of all on this piece of wire down here, this section of wire down here, and you can see if I was to reach inside and grab that piece of wire, so that piece of wire is in my hand here, okay, and I would have the magnetic field because the tips of my fingers indicate the magnetic field coming out of the page. So if I do that like that, then the tips point towards me, and that would produce this magnetic field that's directed out of the page. Remember, X's mean in, these little dots mean out. So if I do that, then my thumb points in the direction of the current. You can see if I was having more in, my thumb would point in the opposite direction. But I want to have more out, so my fingers would be inside the coil, indicating magnetic field out of the page. My thumb points to the right, so that's on the right-hand side. That's on the bottom. The current would be flowing to the right. This is my right. Okay? Now, I can do that for all 4 sides. If I look at the gray bar now, I can reach inside and hold the gray bar in my hand, and the magnetic field would be coming out of the page. That would be the part that's inside the coil, and my thumb would be pointing up. Now, on the top part of that wire, Okay, I reach inside now, and my magnetic field points out, and my thumb points to the left. And on the other side where the resistor is, I do the same thing, and the magnetic field is coming out. The resistor would be flowing through here, and the current is pointing down. My thumb points down. That's the direction of the current. So that means that in order to produce a magnetic field that would be coming out of the page, the current, the induced current, would have to flow in the counterclockwise direction. So the direction of the current in this case would be counterclockwise to oppose that increasing magnetic field that's pointing in. All right, so now we did that. Okay, that's the magnitude and the direction, and now we're going to determine the magnitude and the direction of the force needed to move the bar. Now this is the bar. The bar is moving through this magnetic field, and inside the bar there's charge. And we said in the previous slide that in the bar the current flows up like that. We want to determine the force and the direction, the magnitude of the force. Well, let's do the direction first. So once again, I'm going to use my right-hand rule. This is for the Lorentz force on the charges that are inside that bar. I'm going to point my thumb up because it points in the direction of the current again. My fingers point in the direction of the magnetic field. The magnetic field is directed into the page. That's what those X's indicate, that the magnetic field points into the page. And then my palm points, so to speak, in the direction of the force. That's the direction of the Lorentz force. That's not the direction that I would need to apply. So the Lorentz force is to the left, like that. This is my left. And that means if I want to move that bar at a constant velocity through that magnetic field, I'm going to have to apply a force that's equal in magnitude but opposite in direction. So the Lorentz force points to the left, and the force that I would have to apply would be to the right. And it would be an equal force, equal and opposite. All right? So that is the direction of the force. Now, to calculate the magnitude of the force, we use this equation. I like to call this the Bill equation. This is the F is the force, Lorentz force. We're actually calculating the Lorentz force. And this is the B is the magnetic field strength. This is the current, and this is the length. And it's the length of this bar that's crossed in this magnetic field. Now, this L is the lowercase l, because usually in the equation you see it written as a lowercase l. But it's the same L over here. This is the length, so that's 15 centimeters. So we just plug those values in, 5 teslas, magnetic field strength. We calculated on the previous slide that the current was 1.15 times 10 to the minus 3 amperes, and that this is 0.15 meters, okay? This is 15 centimeters, convert to meters. And just multiply those values, you get that the applied force, the force that you would have to apply, well, actually you're calculating the Lorentz force, is 8.6 times 10 to the minus 4 newtons, and we would apply a force equal but opposite direction to pull that bar through that magnetic field. Okay, so there you go. That was questions 5 and 6. You can link to part 1 in the upper right-hand corner again. I hope you found that video helpful. If you did, please do all the following 4 things. Subscribe to my channel. Get all my excellent physics, chemistry, and math videos. Give me a thumbs up for this video. Leave me a nice and positive comment in the comment section below. And don't forget sharing this, share this video with all of your friends. Show them how much you care. Thanks for watching. We'll see you in the next video.